Welcome to Tic-Tac-Toe the Hard Way, the podcast in which a writer and a software engineer train an AI to play a simple game.
And take a hands-on approach to exploring the very human choices that go into training a machine learning system.
And welcome back to the podcast. Hey, David.
Hi, Yannick.
How are you doing?
So the project has been going pretty much okay for me, my side of it.
Excellent. I expect you have some data for me then.
I just don't know if it's the right sort of data. How many random games of tic-tac-toe do you want? Because I got a lot.
Okay, we'll get into it. But let's maybe first do like a really quick recap of where we were last time and how we ended up where we are today. So as I recall, we are trying to train a machine learning system to play tic-tac-toe as a stepping stone to playing a more complex variant that we have dubbed tic-tac-toe. Is that correct?
That is my understanding.
As part of that journey, I went away and created a little viewing environment so that we can see these agents actually play each other in the game of tic-tac-toe. And you went to create some data.
I did.
Do you want to tell us more about that data?
It is so fascinating.
As data always is.
I actually agree with you, but I've been generating randomly played tic-tac-toe games and saving into a file in the JSON format games where there's a winner. So not ties, and all the games, because the way I've structured it, the way that the games are generated, the computer always picks an available random square. It doesn't try to put a mark into a square that's already taken, that sort of thing. And because it's playing randomly, a whole bunch of those games end in ties. They just sort of peter out. The only ones I'm saving are the ones where somebody won, and I'm recording who won it. And because it's easy enough to do, my data files, which are in this JSON format, have a whole bunch of information I'm pretty sure is irrelevant, but why not?
Yeah.
And the idea is, just as sort of a recap, I'm going to be training a machine learning system to play tic-tac-toe using the supervised learning method. And you are going to be using a different method.
Yes, reinforcement learning, which doesn't sort of require a pre-generated data set, but it does require this environment that it can interact with and that it can play the game against. And we'll be talking about that, I think, in future episodes. I think we're initially going to focus on your agent and getting that up and running.
Yeah, which, given that I am not anywhere close to being a computer scientist or developer, is likely to take me somewhat longer, let's say, than the work you're going to do.
And it's also generally sort of a easier scheme to understand. So it's a good place to start in terms of picking machine learning schemes. If you hear about these terms, supervised reinforcement learning, and there's a way to do it supervised, generally that's going to be simpler. So folks may want to start there.
So as I understand it, in supervised learning, what we want to do is give the machine learning system a whole bunch of examples, data that are examples that have been labeled about what they are. A common example is, which we talked about last week, is training it to recognize images of animals. You feed in lots of images of animals, but each of which has a correct label saying what animal it is. And you hope that the system will learn to recognize patterns, some of which may not be apparent to humans, that will enable it to sort the images into the labeled bins, so to speak.
Exactly.
Good. So that's easier to understand, I think, than exactly how that's going to work for tic-tac-toe.
Yeah, and that's essentially one of our main topics today. How do we get that similar structure of data that you described for the image classification problem? Like, how do we do that for a game like tic-tac-toe?
So I've been generating these randomly played games.
How many did you generate?
I went up to 15,000, but I've got lots of different sets with different amounts. You said last time, 5 to 10, that's a good guess. So I figured I'd do another.
Switch it up a little bit.
Yeah, a little bit.
Yeah.
They only include games in which there is a winner. I note who the winner is. I don't know if I need to do that, but I do. Which player. I also note each game, which players went first. Was it X or O?
Yeah.
Which seems like it might be relevant.
And these are all the things that are recorded in your file. Like where you're essentially taking a tour of the file that you generated and seeing what's in there.
Yes, and I know just how fascinating a tour of the file of data that I generated must be.
I live for the such tours.
Okay, so let's say it's a 10,000 game file.
Mm-hmm.
Each game consists of a set of moves. Each move has a set of data associated with it.
Okay. So yeah, we have a list of games, and each game is a list of moves. And what's in a move? What's that data associated with it?
Again, probably too much, but it includes the board state, that is a representation of the board that the player who's making the move saw. So the first move is a blank board.
And how did you represent that?
I did it as a string of 9 characters.
Okay. Quite reasonable.
Oh, good.
Quite reasonable.
And these strings, I figure the characters don't matter, but if it's a blank, it's a dash. If it's an X, it's an X. If it's a O, it's an O.
That makes it very readable. Thank you for not choosing like other symbols.
I was going to go with emojis.
Yeah. Well,
But yeah.
Good luck emoji debugging.
And spaces, of course, would have worked instead of dashes, but it is much harder for the human eye to read.
Yeah, especially you have to count them.
Yes. Yeah.
So I think you made some wise choices there.
Excellent. That's what a board looks like.
Yeah.
And then because we want to train it on when the system sees a board in some configuration, one of these board states, we want it to come up with a move. So for each move, there's the board that the player received and a board that after the player made his or her move, and I also, because why not, include the square that the player moved.
Okay.
Right.
So you have a current board string.
Yes.
And then a next board string.
Yes.
And then another value that is what is the board position that got played to.
Yeah. So if the move was square 7, it says 7.
Okay.
Also, who won the game
Who won the game? Yeah.
and how many moves it took for the whole game.
Okay.
It would seem to me, based upon my intuition, which of course is totally unreliable, that we want it not only winning games, but to be winning them as quickly as possible. Because if they don't, then they're giving the other player an opportunity to win.
Yeah.
So
Maybe we'll be able to use that.
I also include the move number in that particular game. So
Okay.
I
Which is
figure,
basically sort of like the position in that list.
yeah, in the game list, yes.
Okay, cool.
Yeah. I configure that the initial board state and the board state that reflects the move the player made or the number of the box that the player played into. I think those sound like they got to be
This
there.
is good. It sounds like you generated some data and you tried to collect everything that you thought might be relevant or useful.
Yes.
That's great. We have this like rich data set, and now we sort of have to turn it into something that we can learn from. So there's a couple of words that you mentioned that I want to sort of dig into and talk about. One of which is input and another is label. We sort of described supervised learning as needing labels. In the image classification case, it's things like zebra or tiger. So what does that mean here? I'll try and sort of give a description of it, and we can dive into it in more depth as needed. So on one side, we have inputs, and that is the thing which the model will look at in order to make a prediction. And I'm going to explain what a prediction is.
You can see the concern on my face.
Very concerned. And it's prediction because we want to train it so it can play the game of tic-tac-toe later. So you can think of it as like later in that scenario when it's in the arena and it's faced with a board, it has to make a prediction about what to play.
So this is not the way we usually talk about predictions.
I don't talk about predictions all that often outside of machine learning.
Yeah, well,
So tell me more.
well, if I'm going to predict the weather, I'm making a guess at what the weather will be. I'm predicting the weather because I don't know. I'm not responsible for the weather. If I was in charge of the weather, I wouldn't predict. I would say tomorrow is going to be sunny. That wouldn't be a prediction. For us, a prediction, for normal human beings, nothing personal.
I take offense.
To call getting a label of a tiger right in the image example or the best move to make is not really a prediction.
Well, maybe I'll say this and maybe it helps. One way to think of it is the model is going to make a prediction of what move you should make. Ultimately, you're still going to have to write a program that takes that prediction and decides whether to do that thing. So it's essentially a prediction that this is a good move to make. That's one way to look at it that maybe matches it with that sort of more colloquial notion of prediction. Another way to look at this, and this may be not as helpful, is prediction isn't the only word we use for it. Sometimes we just refer to this as an inference. But I don't think we really need the extra jargon term.
It's a little
We can
clearer,
probably
though, right?
just stick with prediction or inference, which is another very commonly used term for that same thing. So you can think of them as synonymous when we're talking in ML jargon.
So is it only a label when it's the input data that's training the system?
Yes. So when the label part comes during the training part. So we know in future we want to be able to make predictions or inferences, but right now we have to teach it. And for that we need labels. So a label is the ground truth of what you want the model to do at prediction time in the future. So it is, for a given input, what is the answer that should be given?
Okay, good.
That's what a label is.
And just to be clear, ground truth, it sounds like absolute truth. It sounds like the thing that can't be denied. But if inputting the data, you mislabel a tiger as an elephant, that's still ground truth to the system.
This is definitely lowercase t truth.
Okay.
It is ground truth as a human input it, with all of the human's decisions and knowledge and lack of knowledge embedded in that.
And typing errors.
Yeah.
So
happens all the time. So yeah.
Judgment calls. So it's ground truth for the machine because the machine has no way of looking outside and investigating it.
That's what it's been told. It sort of just takes it.
I thought they were supposed to be smarter than us.
We're going to clear up that misconception. So that's what we want to generate. We want to generate these input and label pairs. And that's the teaching it by example. For every board state, we want to be like, this is the move you should make. So we have to find a representation that's like, that's the thing we want to predict. And that's what a label is. Are you with me?
I am with you for now, at least for the next few minutes until I forget the distinction. So, okay, good.
Okay. So let's talk concretely about turning the data you just talked about into those pairs. So what we need for training is we need the input and we need the label. So what's the input for you?
So I want to ask you a question.
Sure.
I carefully maintain this data structure of games with moves in them. And I had to play through games in order to find out if there was a winner and who it was. I couldn't just generate random moves. They have to be in a game, right? Okay. Do I need the games anymore?
So that's a great question. And I would say you don't need them. But we should talk about why. And, there might be some ways to use them, but you probably don't need them. And
we need the moves in the game.
We need the
moves. We don't
in
need
the
the
game.
structure of the game around. We don't need to know what game a move came from.
Yes. So, David, if I brought you a tic-tac-toe game that is partway through being played, let's say we're on move 4, do you think you could effectively make the next move?
Yes, I do.
Do you think you need any sort of information about like how we got to that particular state of the board?
No.
Yeah. Given your expert level knowledge of tic-tac-toe, given a board state, you can make a reasonable next move.
Yes.
So based on that, I would argue we don't need to have the structure of the game. There may be situations in which you could try and take advantage of that. But in this situation, it seems like you don't need that extra data and that extra complexity. So we might want to see how far we can get with just looking at a board and trying to say, given a board state, what should I do next? And sort of discard the notion of it being in a game, as strange as that may sound.
It does sound strange, but it sounds right. It makes complete sense to me. That's all that the machine needs. It is a very different way of thinking about a game, right? Because we think about games as a series of moves, and it turns out, they can just be moves, as long as you know the outcome of the game and thus know that it was a game that had a winner.
Because for most part, our experience with these games are sort of embedded in time and in the whole game play state. And for example, the reinforcement learning approach will actually take that more into account. But for many games, you can think of them as individual puzzles. You can think of each step as just an individual puzzle with a solution. Those add up to a game. But the machine doesn't need to know that in order to be effective at the individual puzzles. It might be able to take advantage of that, or you may try and get it to learn from that structure, which is what we try and do in reinforcement learning, so we don't have to tell it each step of the way. But, maybe it's just, you can just think of it as a series of puzzles.
Okay, so I can extract the moves from the game structure, just have a big pile. I have 10,000 games. I have somewhere between 50 to 90,000 moves.
Okay.
Right? Because there's 9 possible.
Yeah, you'll count them up. So those will be your inputs.
Okay.
Correct?
Yes.
Now, we have to talk about what the label portion of this input label pair is. Because for each input, we need a label, that sort of ground truth with a lowercase t. So what do you think the label would be?
So I think it should be either the string that represents the state of the board in the next move or the number of the square that gets occupied. And I can see made up reasons for either one of those.
Mm-hmm.
The representation of the board, the full 9-character string, that's sort of, I'm thinking like a human, I'm sorry, but you have the input one, and then you have another thing that's very much like it.
Mm-hmm.
There's just one character. It's a string of characters, there's only one that's different. So I'm pretty sure this is wrong. If you were a human looking for patterns, you'd make the grids, the 3x3 grids that we play, not this 9-character string. And I think it would help us to be able to see the next pattern. Maybe that's how we would learn, whereas the number that represents the change in the board is way more abstract. So if I were going to train a human the way we train a machine, probably the 2 boards. I, of course, have zero idea whether that's actually going to be helpful or whether just the number of the next move would be enough.
Yeah, it's a good question to ask. And there you're essentially saying sort of as a human looking at using your visual system, because if you're trying to learn this game without a visual system, you may take a different approach. But with your visual system, you say like, oh, I want to compare these 2 boards and see what changed in the structure of that. And it's easier to do than when there's both of these diagrams than when one is a number. Even though we know they're equivalent, but one is easier on our visual processing system and can take advantage of that. So that's a good intuition. In this case, but do you agree that they're equivalent information? The information is there.
You can derive one
both.
from the other.
Yeah.
Right? So
exactly. So it's just which one is easier for us to process. So here, we just have to ask ourselves, what is easier or maybe necessary for the machine to process to get this out? And in this case, I would say it probably doesn't need that full structure of the previous board. I would suspect, because computers are very good with numbers, as we all know, I would suspect it can do it from just the number. Saying like move to board 4 is not challenging for a computer to conceptualize, for lack of a better term. But yeah, you could use either one, but I would start with a simpler one. And that's another general thing in doing these kinds of projects, like start with the simpler one. So 4 is simpler than the next board string. So see if that works. And then you can do an experiment to see if using a different representation gives you better results, to see if that extra representation was useful. But I suspect it's not needed.
may I say something about the weirdness of this whole input thing?
Sure.
So for each move, the board is represented as a string of 9 characters, right? For something I was writing, I made a list of all the winning boards. There's only a handful of them. And if you write them out as strings, is these 9-character strings, and you just assume that the thing that you would naturally do in this case, which is the first 3 represent the top row, the next 3 are the second row, and the third is the third row. And that's arbitrary, but that's the way, I think humans generally would do this. And you just see, what are the ways I can get 3 in a row on a board and translate it to those strings? They don't exhibit any obvious similarity. The way that you draw the winning lines on a grid, on the 3x3 grid, and it's pretty clear it's 3 in a row. Mm-hmm. But they're winning boards that are absolutely not 3 in a row when written out as not. Which means that the machine learning system is missing some information that's crucial to human players. It's crucial to us as humans that it's a grid, that there are corners, that there's a special center, and the special center may be more or less useful, and the corners our way of playing is all based around what we've learned about this grid, not this seemingly arbitrary set of 9-character strings. The machine's not going to know anything about corners. It may figure out that playing a corner is statistically more likely to come to a win. At least I think it should do that. But it doesn't know about corners.
Yeah, this is a great question about input representation. You recorded these games as that string of characters. Is that the best way to feed it into the system, or does it need that geometric representation, that 2D? I would say it's quite useful for us as humans. I can imagine somebody could learn to play effectively with just the string representation. It would just be hard. It would be super hard. And it would not take advantage of a bunch of our visual faculties and other stuff.
And what constitutes a winning string will seem to us to be just arbitrary. And you can memorize them. As I say, it's only a handful of them. No, but it's just, at that point.
I wouldn't say it's arbitrary. If you learn to play with just the string representation, you will begin to understand the patterns.
Maybe. You'll understand the patterns. You may never realize that, oh, if I did this as a 3x3 grid, I would see that it's drawing straight lines across,
I'm
So
not
in
saying
sense,
that you would
arbitrary.
need to make that mapping, but I'm saying like a human might be able to learn it even with a string representation
Yes.
in a
Oh,
way
yeah.
that's not arbitrary
Yes.
and it's not memorization. It's just learning a different kind of mapping and different relationships that's one-dimensional instead of two-dimensional.
Yes. In fact, my board representations start first row, second row, third row, but I could have done it backwards. I could make up a random order for the squares so long as I consistently applied it across all of them.
Yes, you could. As
Yeah.
long as it's consistent, you can learn a pattern from that. And you just
Okay.
need the machine to learn that pattern. So flexible input representations, which is really handy actually in machine learning.
And weird for human learning. So,
Different.
Yeah.
Different.
Well, I'm going to take us as normal and them as weird. I'm a little human-centric. Okay, so where are we for next week?
So I think now, do you feel like you have a good sense of what the inputs and labels are and how you are going to make them?
I do.
So if you could just very briefly describe, so you have your current file with the games. Based on what we've talked on, what's the new file that you need to make? And just vaguely, what does it look like? What are your inputs and what are your labels?
Okay, it's a list of moves where a move consists of an input, which is the board state as the player sees it, and then the number of the box that is that player's next move. I think I also need to include which player won the game that it's in.
You could, I would keep that around, and we can talk more about what goes into the training. I would also probably keep around who's playing currently, who made the move. Might be handy.
Yep.
Might not be necessary, but might be handy to keep around, just sort of in this flat list.
Okay.
That sounds great. Excellent.
Okay, now
So with that, that means the next time we meet, we'll be able to talk about like how we take that data and actually train something, and sort of what's the thing we built and how we train it. But that's the form of data we're going to give for the training process.
excellent. And what are you going to do?
I'm going to wait and see what happens with you and try and help you along the way.
Okay.
But yeah, I'm sort of working on the side on this reinforcement learning thing, which there's probably more detail about that than I can sort of summarize here. So I'm probably going to defer some of that stuff until we talk about that one.
I'm happy to carry you,
I
until-
welcome that. I welcome that. It's tough out here.
Okay.
All right, excellent. See you next time.
Yes, you will.
You've been listening to Tic-Tac-Toe the Hard Way with your hosts Yannick Asogba and David Weinberger. This is a production of Google Pair, with thanks to Rebecca Salois, Eric Johansson, mixer and editor Brian Gordon,
And the entire Pair team of developers, researchers, designers, artists, philosophers, and more. A special thanks to Nikhil Thorat, who created the music with help from AI by Google Magenta.
You can find links to code and more in the show notes and at our website, pair.withgoogle.com/thehardway. Once again, that's pair.withgoogle.com/thehardway.